Hi, and welcome to our presentation and demo about building internal developer platforms, leveraging the power of Kubernetes operators. My name is Dan McKean, and I'm a product manager at MongoDB, and I'm joined by George Hantzaras, who's an engineering director, also at MongoDB. Together, we're responsible for enabling our customers and users to run MongoDB in two ways: self-hosted in Kubernetes using our enterprise or community Kubernetes operators, or using our Atlas Kubernetes operator, designed to manage and configure our Atlas developer data platform.
In our presentation, we'll start with a brief introduction of internal developer platforms and what we defined as platform capabilities and platform interfaces. We'll talk about the rise of Kubernetes as the first choice of underlying platform infrastructure and how its extensibility has made this possible. And finally, we'll see a brief demo of how operators can be leveraged to build platform capabilities and platform interfaces.
So, as George mentioned, we're going to start with a look at internal developer platforms and the rise of Kubernetes. Internal developer platforms, or IDPs, bridge the gap between underlying capability providers and platform users, such as application developers. In doing so, platforms implement and enforce desired practices, often described as golden paths. An IDP offers various integrated capabilities, usually from a variety of tools and services. This includes things like continuous deployment workflows, observability tooling, managed databases, secret management services, and more. These tools, services, and golden paths provided to simplify tasks are usually available through a variety of interfaces, including CLI, GitOps tooling like ArgoCD or Flux, or a developer portal like Backstage. While there's not much data to categorically prove that the majority of IDPs are built on Kubernetes, it seems to be the consensus that Kubernetes is winning as the platform of platforms. But Kubernetes hasn't always been ideal for an IDP. There have been a few key developments. Extensibility improvements now allow Kubernetes to do more than just orchestrate containers. They can manage applications like databases, security systems, and other cloud-native components. As well as extensibility, the Cloud Native Computing Foundation has fostered an amazingly rich ecosystem of tools and services that can be deployed and managed on Kubernetes. And standardization and abstraction have played a big part. This has meant that Kubernetes has become far more interoperable, and abstraction has drastically simplified management to make it easier to use.
Now we're going to dig a little into one of the most critical evolutions in Kubernetes, one that arguably underpins both the thriving ecosystem and many of the latest abstractions that simplify use of Kubernetes. So Kubernetes has a number of inbuilt controllers. They automate management of different tasks like replicating pods, exposing pods externally through services, and management of namespaces in Kubernetes. Each controller follows a control loop. They check the desired state, compare it to the current state within Kubernetes, and then reconcile to make changes to ensure that the current state reflects the desired state. And while the default controllers are entirely critical for Kubernetes to function, it's custom controllers that provide the extensibility. So custom controllers allow to extend what types of tasks and resources Kubernetes is capable of orchestrating. They work in conjunction with custom resource definitions, CRDs, to manage custom resources specific to our needs. Custom resource definitions specify the schema for a custom resource. This essentially creates a new type of object that the custom controller runs in Kubernetes, and it can be recognized and managed.
But what are Kubernetes operators and how do they fit in with custom controllers? Operators package up custom controllers and more to make it easier to deploy and manage custom workloads in Kubernetes. This includes packaging things like various CRDs, code for multiple controllers, Helm charts, and monitoring or diagnostic tooling to make management easier. By bundling these elements together, operators offer a self-contained unit for simplifying management of an entire application within Kubernetes. So why are operators so useful? They simplify application management by providing a single interface for deploying and managing your applications throughout their entire lifecycle. They do that using a declarative approach. So instead of writing complex deployment scripts, you simply define the desired state for your application. They help reduce errors by automating manual tasks, minimizing the risk of human mistakes. They come in standardized packaging and promote a consistent way to package applications. This standardization makes them more portable and reusable across different Kubernetes environments. Operators are designed with domain-specific knowledge and particular types of applications, for example, databases or messaging systems. This expertise ensures that the operator manages an application's intricacies. And there's a rich ecosystem of operators already for things like databases, such as MongoDB, monitoring tools, and other components, saving you the time and effort to learn how to run them in Kubernetes from scratch.
But not all operators are alike. So Kubernetes operators can be broadly categorized into two types based on the resources that they manage. So internal operators focus on managing resources that are entirely running within the Kubernetes cluster itself, while on the other hand, external operators extend Kubernetes' reach by managing resources that reside outside of the Kubernetes cluster. By leveraging the appropriate operator type, you can effectively manage both internal Kubernetes resources and external dependencies in the same way.
Now we move on to arguably the most exciting part. In our demo, we're going to focus on just one element of an IDP using Kubernetes and operators. To show that, we're going to demonstrate how to build database as a service into your IDP. We're going to use an external database as a service, MongoDB Atlas, and integrate it. Atlas is a software as a service offering value as a developer data platform of different complementary tools, including search, analytics, support for mobile applications, as well as different data types, such as time series and geospatial data. It even offers multi-cloud global distribution and resilience. We're going to use the Atlas operator. Since Atlas doesn't run in the Kubernetes cluster, it runs in the hyperscalers. The Atlas operator allows you to use declarative configuration files that can be applied into Kubernetes, where the Atlas operator picks them up and makes changes to Atlas for you via the Atlas admin API. The benefit being that you can deploy your application and Atlas configuration in exactly the same way into Kubernetes using the same tooling. We'll also build a GitOps interface using ArgoCD as the mechanism to bridge the gap between the infrastructure as code files in your repository and Kubernetes. This gives us a highly automated and standardized GitOps workflow, and in doing so, cuts down on the expertise and permissions that individual teams need, as no more direct interactions with Kubernetes are necessary.
So in our demo, we'll start by creating a GitOps platform interface using the ArgoCD operator. And then we'll build our DBaaS capability to deploy databases on Atlas using the Atlas Kubernetes operator. So the first step installing ArgoCD is pretty simple. We'll start by creating our Argo namespace. And then installing the Argo operator is automated by a simple install script, and it's just one command and a few seconds to install. So we can see all of the operator pods for ArgoCD are running in the Argo namespace. Next, we need to create an Argo application resource where we'll define the Git repository that ArgoCD will be watching to find our new files, as well as the destination Kubernetes clusters and namespace for resources to be deploying. Now, going into our Argo UI, we can see our DBaaS application has been created, our application interface, where we can easily monitor sync status. Now, from this point onwards, everything happens through that interface. So to deploy an Atlas project, we use an Atlas project custom resource. And all we have to do is a simple git push in our infrastructure as code repository. As we can see in the Argo UI, our Argo application has picked up the changes in GitHub and has created the Atlas project custom resource in Kubernetes. Now, under the hood, the operator has picked up this custom resource and has created the new project in Atlas using the Atlas admin API. Back to our editor, again, we're going to use a simple YAML file to deploy a cluster. The type is Atlas deployment, that's our resource. And again, a simple git push. And all of the magic happens under the hood. The ArgoCD application picks up the changes in our Git repo, deploys the custom resource in Kubernetes, and that is picked up by the operator, which in turn deploys our cluster in Atlas. Now that we've streamlined the deployment and management of new databases, we'll see how easily we can enhance these capabilities through operators, and we can see how easy it is to connect application to our resources in a Kubernetes native way. We'll be using a new custom resource called Atlas Database User in order to manage database access. Each Atlas database user is just another file in the repository, so the operator will make it very easy for us to manage it. So we've already created a Kubernetes secret that contains our user password. And we use a simple custom resource definition for a database user referencing this password. As we did before, we'll use our GitOps interface. And ArgoCD will pick up the change and deploy the Atlas database user resource in Kubernetes. Now, additionally, the operator in the background for this resource creates a new Kubernetes secret named after our project, cluster, and username combination. This secret contains all the connection information that our deployments will need in order to connect to our databases. Now, if we explore the secret, we can see that we have the connection string for our Atlas deployed database. Now, for the last part, we'll create a very simple Kubernetes deployment. We'll be using the Mongo image to run a Mongo shell and connect to our database in Atlas. So our application here reads the secret and uses it as an environment variable in order to use that connection string and connect. We simply deploy this deployment using kubectl. And now we can see that our Mongo shell pod is running. And inspecting the logs of these pods, we can see that the shell has connected into our Atlas cluster. Now, as this was the end of the demo, I'm pretty sure that you might be expecting fireworks towards the end of a demo. Now, the good news is that when it comes to managing infrastructure in critical production environments, not having fireworks is a good thing.
And that's it. Through this link or the QR code, you can find a landing page that gives you all the information that you need to replicate our demo, or even to take the next steps and start building MongoDB Atlas into your IDP to provide a database as a service. Thank you very much for joining us.